Okay, in chapter 26, we're going to be looking at part 4, in which just the eye and our vision. Okay, so we have a um, lens in our eyes that helps to focus light at the back of our eyeball. So we've got an object that we're looking at. Light is radiating out from this object in many directions. Some of them enter our eye and go through our pupil, and then the lens helps to focus that light at the back of our eyeball. And at the back of the eyeball, there are cells called rods and cones. And cones predominate right here in this area, um, and rods predominate more at the edges of our vision. We've got more rods here and here. Now, what happens is those cells detect light, and so they detect the light that's coming in, and they send those signals along nerves and out through the optic nerve. And so, just like a wrist has to be free to move, so does our eyeball. And so, all of these signals go through the same thick branching pathway. So, our eyeball is free to move. Um, and so, then that goes to our brain. So, the optic nerve uh, makes a blind spot in our eyeball. And so if you look at this black dot with your right eye and move your head towards the screen or towards the page in your book, the X that's over here will actually disappear from your vision because it will pass into the optic nerve. Okay, up there, that's the right distance for me. So it depends on how far away you are and how big it is on the screen. So try that. It's in your book. And the thing is that this could be a real problem if this blind spot affected our vision. But the thing is that it's in a different location for our right eye and our left eye. You can try this with your left eye, stare at this cross, and the dot will disappear. Um, but the thing is that because they're on opposite sides of our eyeballs, then the brain just has the eyeballs fills in that spot for you. So it takes the view from the left eye and fills in the blank spot on the right, and vice versa. Okay, now these cells that are called rods and cones that detect light are cone shaped and rod shaped. And the rods are useful for detecting mostly just the presence of light. So there are more primitive type of vision. They don't care about color. They just say, hey, there's light here. This is how much there is. So it gives us kind of a grayscale vision or black and white vision. Now, this is very useful because they're primitive, but because of that, they don't take much energy. So these are the ones we use when we're stumbling around in the dark, and we may not care what color things are at that moment. We just want to avoid running into them. So, but it's also one reason that when you're out in the parking lot or something, you're having trouble finding your car, you can't tell what color it is because your cones aren't working. They take too much energy. But your rods are working. Now, rods also are good because they don't take much energy. They work faster than the cones. And so these are the ones that catch the car coming out of from the side who's run the light. Those are the ones that save your life. So the rods are really useful for that. So when say we see something at the edge, we caught it out of the corner of our eye, that's when we're talking about the rods. And so, yes, these definitely can save your life. Save mine. Anyway, I was with a bunch of kids crossing the street. We just gotten off the school bus, and I caught the car out of the corner of my eye and managed to get everybody to stop. So anyway, as this black car went barreling across the intersection. Anyway, so yes, so rods help save your life. Okay, now the cones are um, in three different types. They're called the red cone, the green cone, and the blue cone. They're their nicknames. The red cone is sensitive to low frequency light. So it's sensitive to reds, oranges, and yellows. The green cone is sensitive to the middle frequencies. So it overlaps the red, and that it's sensitive to yellows and lime greens or chartreuses and greens. And it also is sensitive to cyan, the bluey greens. The blue cone is sensitive to the higher frequencies of light. So it's sensitive to the cyans, the blues, and the violets. And so anyway, so it's very useful. We have these three cones, and our brain combines the signals from the cones. So when you're looking at an object, the color you see is your brain has processed those colors and selected a color for you to see. So it takes the signals in, selects a color. So if you get signals from all three cones equally, you will see white light. So when you're looking at this area on the computer screen, which looks white, well, of course, the computer manufacturers and TV manufacturers figured out that people didn't need to have all colors coming from their TV. They just needed to have enough to stimulate your brain. So RGB monitors are red, green, blue monitors, and that's what most computers and phones are and televisions. And so what we've got here is in this white area are pixels that are red, green, and blue. And that's what we're seeing as white. So everything that we're seeing is made up of red, green, and blue pixels, and the computer figures out what is needed to stimulate our brain to see the right colors. Now, so here's sort of showing the cones overlapping, and you can see how the green cone, okay, and the red cone overlap a lot. The blue cone is off over here by itself more. So there's a huge amount of overlap. And later we're going to talk about colorblind people a little bit. What happens is that often these cones overlap so much that people become red-green colorblind. They can't tell the difference between the reds and the greens. Okay, so when light enters our eyes and is detected by the cones, then our brain gets those signals and it figures out a color to tell us that we're seeing. So if you get signals in the red cone, the green cone, and the blue cone at the same time, your brain figures, hey, that's all the colors, that's white. If you just get a signal into the red cone, then your brain tells you that's red. But if you get a signal into just the green cone, your brain will tell you it's green. If it's just in the blue cone, your brain will tell you it's blue. But if you get signals in both the red and the green cone at the same time, then your brain figures it's probably yellow because yellow is detected by both cones. So you see yellow. And now, if it's supposed to be orange, then what will happen is that the signal will be stronger in the red. Make that a bigger one. Okay. So it's going to be stronger in the red. And that shifts the brain over to saying, okay, well, maybe it should be orange. Okay. Because orange would show up in both cones, right? Orange is detected by the red cone and by the green cone. But if you get a stronger signal in the red, then that's going to shift it over from just the yellow, which is also seen by both of them. Okay, so anyway, so there's a huge overlap between the green and the red cone. Anyway, now if the brain gives you cyan, it's because it got signals in both the green cone and the blue cone, because cyan is detected by both blue and green cones. Now, magenta is a funny one in some ways, because if you get a signal from the red cone and a signal from the blue cone, your brain says that's magenta. However, there is no magenta detector. Magenta is not a color of light that human brains actually detect. There is no wavelength of magenta. It's merely in our brain. So magenta or pink is actually just an artifact in our brain. And our brain sees that when it has signals in the red cone and the blue cone at the same time. And of course, you get shades of purples and stuff again by having more blue or more red. Okay, so anyway, I have a demo for this, but it doesn't come over the um, camera at all well. So unfortunately, we can't do it. Okay, so anyway, but you can add up colors in a sort of color wheel thing, and it's called color addition. It's called additive um, colors for light. Okay, so for light, when you add colors together, it's called additive. We're going to look at subtractive color mixing later, but additive color mixing is what light does. And so again, red and blue makes magenta, red and green makes yellow, blue and green makes cyan. And this color wheelie thing can be very useful, so you should learn to um, be able to draw one, so just have your useful to refer to. So red, green, and blue. And then, red and green makes yellow, red and blue makes magenta, green and blue makes cyan, and there's always going to be white in the middle. Now, our brain is detecting the colors of light that the sun is putting out. Okay, that's what our eyes are detecting. So the visible range is where the peak of the sunlight is created. Okay, and it peaks kind of in the yellowy greens here. Okay, so we talked about that before, whereas the Earth produces infrared. Now, because our brain does a lot of processing, then you get weird things like this. This picture came out and people went a little bonkers over it a few years ago. And the reason was that this original photo was seen in two different ways. Around 70% of people saw it this way, as a white dress with gold. But then that left about 30% of the people saw it as this way, a darker blue and black dress. Okay, so what was going on? Well, the picture was bad. The original picture was a fairly bad photograph. So the thing is, your brain thought it needed to process it. It knew it was outside because of all the glaring light. And when your brain has an outside image, it takes away blue because blue is in all the light from the sky. So your brain automatically subtracts that. So what happened was about 70% of people, their brain started to subtract the blue away from the original picture. And so because of that, it left it looking white and gold. But about 30% of people, their brains didn't subtract the blue. And so they interpret it as the blue and black dress, which it really is. So this is the original dress, this blue and black dress. Now, if you squint at the original picture, the colors can start to look darker. I'm a person who sees it as white and gold. So if you already see it as blue and black, this isn't going to work. But if you squint at it and start to look at smaller areas, then the true color starts to come through. And over here on the right here are the true colors for different patches. So this patch is kind of this grayish blue. This patch over here is this darker navy color, and so on. And so the original colors are, they actually are not white and gold. Now, they aren't really blue and black very well either. The blues are still washed out. And that's why this terrible picture, why the dress does not look like it's original. Okay, so anyway, but yeah, it's your brain trying to process things. Um, so color blindness. This is a flag that has purple or violet, blue, green, yellow, orange, and red. Actually, let me write them there. So there's violet, blue, green, yellow, orange, and red. Okay, all right. But on the right side is a protanopia, which means no red cone. And that actually looks like a blue, blue, and then a sort of yellowy gold, gold, yellow, gold, and a dark gold. Okay, now if you have no green cone, then what we've got is sort of a gray violet, a blue, a weird gray sort of color again, gray yellow, then a yellow, gold, gold. Okay. And if you have tritanopia, which is no blue cone, then it's a dark red, then some weird greeny cyan colors, then a sort of peach color, and then a strawberry color, so pink, and then red. Okay. So anyway, the thing is that, of course, more men than women are colorblind. Um, and there are some advantages to being colorblind. Supposedly, if you're a hunter, it is a big advantage because you're not distracted by the colors and you can see shapes better in the woods. You can spot the deer because you're not fooled by the colors so much. So it is an advantage for the hunter gatherers, and sometimes the people can react more quickly if they're colorblind. Um, anyway, but yeah, for a lot of people though, of course, being colorblind is a real pain. So anyway, you can test yourself online by finding a site with Ishihara color blindness test. And so if you can see the 6 here, then your vision may be normal. But if you can't see it, then you may have some of these other issues. And often color blindness is a result of the green and red cones being overlapping too much. So you may still have the cones, they just overlap so much it's like you don't really have much difference. Now, people like that, which is pretty common, can get glasses that can help with that nowadays. And I think what these glasses do is that here you can see how the yellows and the reds and the greens don't have that much difference between them. So I think what the glasses do is they have filters that filter out some colors on either side of the yellow. So if yellow comes in, you see yellow. And if green comes in, you're going to know it's green because it's not overlapping anymore. And if red comes in, you're going to see red. So the idea is, I think that it separates out um, the cone basically back to where they should be, kind of, so that you get the colors, better color definition. So anyway, it makes a huge difference in people being able to see colors. Okay, now women, in addition to not usually being colorblind, some of them actually have an extra cone. The problem is the fourth cone is usually not very useful because it overlaps the green and the red cone too much. But sometimes it's placed so that it actually is useful. And people will see up to 100 times more colors depending on where it's placed and how much overlap there is. So there's an artist in Australia who actually sees many more colors, and she tries to paint what she sees, and everything is very floaty in color. Okay, now, so as I was saying, your brain processes these things. Like here, these rectangles, you've got one on the left and one on the right, and definitely this one looks darker, right? And this one looks lighter. But are they? If I erase the border, because your brain is very big on borders, because you're trying to find things like fruit or deer or stuff. If I erase the border between them, then suddenly the squares don't look that different anymore. And they actually are the same square, just a little bit darker on one side and a little bit, and then they shade towards lighter on their left side. But you can see now they don't look that much different. So the thing is, your brain looks for edges, tries to find edges, and it tries to find patterns. And so in your book, you've got some optical illusions, and you can go online and look up optical illusions like this one. Do you see these dots in here where the corners meet, the dots? Some light dots, some dark dots. Well, those aren't really there. It's just your brain doing weird stuff. And these, of course, are not actually slanted, right? They are all parallel lines. Okay, so anyway, your brain works overtime to process things, which can be very useful, but sometimes not. That's what an optical illusion is. All right, so that's the end of that chapter. So we're going to go on to chapter 27. Okay.